Hello again from our nation's capital. Now we're going to focus on section chapter 4.4, which has a very famous procedure in linear algebra called Gram-Schmidt orthogonalization. So let's suppose we have a basis like this for R2. One vector is 1, 1, one vector is 1, 2. Remember, as long as they're parallel, any two vectors can be bases for R2, can be a basis for R2. We have our standard basis. We have our standard basis 1, 0, and 0, 1, which is what we use all the time and is most convenient because we can see how any vector is divided into two components, a component parallel to the x and a component parallel to the y. But what if we have a basis that does not consist of orthogonal vectors? Okay, so like this one. Note that the dot product is 3, so the vectors are not orthogonal. We want to orthogonalize them. We want to make them orthogonal. So what we do with this Gram-Schmidt orthogonalization procedure, we just take one of the vectors and leave that vector alone. So let's say v1 and v2 are going to be our orthogonal vectors. So we're going to let v1 be x1. Then what do we do with v2? Well, to get v2, what we do, think about how v1, which is the same as x1, is going off this way. x2 is going off this way, not orthogonal to v1 or x1. So what we're going to do is get the projection of x2 onto v1, and what we want to use for v2 is this vector that consists of x2 minus pv1. pv1 is the projection onto v1. So we're taking off the component of the vector x2 in the direction of v1, and then we just have something in the direction orthogonal to v1. So what we do is we let v2 be x2 minus projection of x2 onto v1 times v1. Okay, so x2 is 1, 2. When we take the dot product of v1 with x2, we get 1 plus 2, which is 3. When we take the dot product of v1 with itself, which is x1, we get 2. So our answer is negative 1/2, 1/2. v1 and v2 are orthogonal components. And you can check that. 1 times negative 1/2 is negative 1/2. 1 times 1/2 is 1/2. They're orthogonal. We might also want to make them not only orthogonal, but of length 1, which is another way of saying we want an orthonormal basis, v1 prime and v2 prime. Not only will they be orthogonal, but they'll both be of unit length. Well, we just have to divide this vector by its length, which is the norm of this vector, which is just going to be the square root of 1 squared plus 1 squared, which is the square root of 2. The norm of this vector, which is going to be 1/4 plus 1/4, which is 2/4, square root of that. So it's going to be 1 over the square root of 2, or we can write it as square root of 2 over 2. So v1 prime means that v1, v2 prime are not only orthogonal, they're orthonormal. In other words, their lengths are 1 unit. So now we have v1 prime is 1 over square root of 2, 1 over square root of 2, v2 prime is negative 1 over square root of 2, 1 over square root of 2. So this is the Gram-Schmidt orthogonalization process. So we need to extend that, though, to 3 vectors, 4 vectors, 5 vectors, 6 vectors. So that's what we're going to do next. Let me get my highly technical system set up here. Okay, let's say we have 3 vectors in R3. Again, any 3 independent vectors could be a basis for R3. Our nice vector basis for R3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1, which are all orthogonal, orthonormal even, not just orthogonal, but orthonormal. That's why the standard basis is so good. But here we want this basis, but we want to turn them into orthogonal vectors. So we do the same thing we did before. We pick one, let's say x1, and make that our first vector. So we're looking for v1, v2, v3 that are going to be orthogonal in R3. So we let v1 be x1. Then we take v2, and now we're going to subtract off the projection of x2 onto v1. So we subtract that off. That leaves us with a vector 2, 1, 1, which you can check. It is orthogonal to 1, negative 1, negative 1. Okay? But what about the third vector? Well, when we have a third vector, we take x3, we've got to subtract off the projection of x3 on v1, and we've got to subtract off the projection of x3 on v2. So we've got to do 2 subtractions. We're subtracting off the projection of x3 on v1. So we're subtracting off the component of x3 that's on v1. We're subtracting off the component of x3 that's on v2. And when we do that, we get 0, negative 1, 1. So this is the dot, this is x3, 3, 2, 4. Negative 3 is the dot product of v1, which is x1, with x3, which is going to be 3 minus 2 minus 4. And then on the bottom is the dot product of v1 with itself, which is going to be 3. So here's that scalar that we're multiplying our vector by. So we get 3, 2, 4 minus this, minus this. So this is just v2 and x3. So v2 and x3, the dot product of v2, which is here, and x3 is going to be 2 times 3, which is 6, plus 2 plus 4, which is 12, divided by the dot product of v2 with itself. And we wind up with 0, negative 1, 1. So here's our new basis that's definitely orthogonal. It's not orthonormal. Each one of these vectors, their length isn't 1. So if we want to make them orthonormal vectors, we're going to have to divide by the length of each. And we can do that. The length of this is going to be square root of 3, so we divide by it. The length of this is going to be square root of 6, we divide by it. The length of this is square root of 2, we divide by it. So this gives us an orthonormal basis. We can take any basis in R3 or any vector space and turn it into an orthonormal basis. So let me do my technical thing here and sum it all up. This is the notation that's usually used for Schmidt orthogonalization. What you're going to get out, given vectors v1, x1 through xk, you want to come out with vectors v1 through vk that are orthogonal. Notice this doesn't normalize them. That's another step if we want to do that. pick the first vector to be x1. The second vector would be x2 minus the projection of x2 on v1. The third vector would be x3 minus the projection of x3 on v1 minus the projection of x3 on v2. The next one, if we had a v4, it would be x4 minus the projection of x4 onto v1 times v1 minus the projection of x4 onto v2 times v2 minus the projection of x4 onto v3 times v3, and so on. So you keep going until your last vector, vk, is xk minus the projection on v1 minus the projection on v2 minus the projection on v3, until you get all the way up to v sub k minus 1. So this is the Gram-Schmidt orthogonalization procedure. You have multiple videos, more videos to watch. One is going to be on QR factorization, Cauchy-Schwarz inequality, which is still referring to chapter 4.4. And then you have lectures to watch on Monday, which are going to be on inner product spaces. So see you again soon.